All right, so here we're going to do a few examples of evaluating limits algebraically. And we've been working with graphs up until now, but we need to know how to do this when we don't have a graph. And the process is really pretty simple. The first thing we're always going to do is to test the value of the function at the value that the limit is approaching. In other words, we're going to just go ahead and plug in, we're going to substitute the value of x that x is approaching here and see what we get. And so in this case we get -6 plus 6, which is 0. 0 is a perfectly good number, and so we can say that the limit as x approaches -3 of 2x plus 6 is equal to 0. Okay, so nothing to it. We'll try it again here on this one. What we're going to do is test the value. Okay, so we'll say that we have 2 times 5 plus 9, and that's going to give us 10 plus 9, which is 19. Once again, 19 being a perfectly valid number, okay, is going to give us 19. Wanted to be sure to have an example with 0 here, because sometimes, 0 is a special number, and sometimes people look at that and say, well, is there a problem that this is equal to 0? And the answer is no. 0 is, again, a perfectly good number. Let's go ahead in this case here, and we'll do the test on this. Now, x is approaching -1, so we've got 13 minus -1 divided by -1 plus 1. And if we simplify this, 13 minus -1 is going to be 14 on the numerator. But on the denominator, notice that we have -1 plus 1, and that gives us 0. And this is going to be undefined. As we'll see before too long, this is actually telling us that there's a vertical asymptote. Remember, if we divide by 0, we get essentially an infinite answer. And so we would say that this limit does not exist, or we could say that it's undefined. Now, in this case, we have a test at x equals 4, and so we'll take 4 squared on top minus 16, and on the bottom we've got 4 minus 4. And so what this gives us then is 4 squared is 16 minus 16. This gives us 0 in the numerator and 0 in the denominator, and this is an indeterminate form. So we don't know what this is telling us here. It's just telling us that perhaps we have to do something a little bit different here. And so this is what we're going to do. Whenever we get a 0 over 0 result, that's different than a number divided by 0. If we have a number divided by 0, we are done. It's undefined. If we get 0 over 0, what this is pretty much telling us is that we might need to look a little bit further to see what we might be able to do to find the solution to this. Keep in mind that when we are trying to find the limit of a function as x approaches some value, and we're trying to find a rate of change, generally we're going to end up with 0 over 0. The reason is because as we move the 2 points closer together and try to calculate the slope there, as we've seen a lot of times before, we're going to get a 0 change in x and a corresponding 0 change in y. And so the 0 over 0 oftentimes just tells us that there's a hole in the graph at that point, and what the limit is trying to find out is basically what would the y value be at that hole if we were to eliminate or fill that hole. And so what we can do is to say, well, what happens if we factor this? Let's take x squared minus 16. This is the difference of two squares, and we know that this will factor as x minus 4 over x, times x plus 4, and then on the bottom we still have x minus 4. So one thing that we can see right away is that we have the same thing, the same factor on the top and the bottom. We can go ahead and cancel that, but before we do, I want to talk about that just a little bit. X minus 4 over x minus 4 is equal to 1, and that's why we can cancel, because basically this part right here is equal to 1, except when x is equal to 4. But remember that when we calculate limits, we don't care what happens at x equals 4. We only care about what's happening as we approach x equals 4. So x could be 4.000000001, and we would have some number that's not 0 on top and some number that's same number that's not 0 on the bottom. This would still be equal to 1. So as long as x is not equal to 4, we can go ahead and cancel this out. And so really this fraction right here then, as we do our test, okay, we plug in, we get 0 over 0, but that tells us, well, let's go ahead and try to factor this. And if we do that, we end up with x plus 4. Well, now we're going to go ahead and try again. So now we've got limit as x approaches 4 of x plus 4. This is what's left over after we've taken care of basically removing the hole here and recalculating to see, okay, if we took that hole out, what would our y value be? And so now we're just going to apply the same test that we had before, where we're going to plug in our value, and that's going to give us 8, and that is going to be the value of our limit. Okay, so when we have 0 over 0, what we have to do is, instead of giving up at that point, instead of saying that it's undefined or does not exist, we need to do a little bit more work. And generally that's going to involve factoring if we have a rational function. So this is really going to be our process here. To solve a limit algebraically, what we're going to do, and I just wrote a generic expression for a limit up here. X is going to approach some number, and we'll call that number c. So the first thing we're going to do is substitute c in place of x and see what happens. Okay? In other words, we're going to be calculating f of c. All right, so a couple possible things could happen. The first thing that could happen is that we get a very good number, perfectly good number, something like 7 or negative 200 or 0. Okay? And if that's true, then that is the limit. Whatever that number turns out to be. Okay? If it's something else, if it's not just a number, we're going to have two possibilities. We may have a number divided by 0, okay, in which case the limit does not exist, okay, because we're basically taking a number divided by 0. But if we end up with 0 over 0, we can try factoring, or we can try other, we'll call them algebraic manipulations. Okay, and that could be using identities or conjugates or some other form of changing the form of the ratio so that we end up eliminating that hole. Generally, for what we're going to be doing here, factoring is going to be the solution, and that's going to hopefully eliminate the 0 over 0. Now, if we're dealing with a piecewise function, okay, and c is the value where the function definition changes, what we're going to do is follow this process for the functions that are on both sides of c. Okay, and we'll treat the two different results as one-sided limits. So from the left we might have, let's say, x squared, and from the right we might have 2x plus 5, for example. We're going to calculate the limit as x approaches c from the left of x squared, and the limit as x approaches c from the right of 2x plus 5. And as we treat this as two one-sided limits, then the limit is going to be equal to the value of the two one-sided limits if and only if they both exist and are equal to each other, so we already know that part. Okay, and at this point then, if we're still getting 0 over 0, we still got more to do, we can go back and start over. Okay, so once we've eliminated possibly some factors that are giving us a hole, we can go back and try again and see if we get an answer. If we don't, we might continue and do some more factoring, some other algebraic manipulations, and so forth. If nothing else ends up working, or if we end up with a 0 over 0, it's possible, or a number over 0, it's possible that the limit doesn't exist at all.